Our problem, and I have done some other problems, but now the problems will be on how to solve it. So this is our circuit, and this circuit has, this is our bipolar circuit. Okay, two terminal bipolar circuit, and this was our ground, right? So if you see that it is saying that 12 pulse converter per pole at each terminal. Okay, and the system is having a data of rated voltage is UD plus minus 500 kVA. So kV. So if it is saying rated voltage of UD, and it is not mentioning whether it is on the right in rectifier side or whether it is on the inverter side, you have to assume that this is on the rectifier side. Okay, so rectifier side the voltage is 500. So this is 500 kV plus 500 kV. You can expect the down part will be the negative 500. Okay, so this is our 500 kV, and then rated bipolar power. So it is said that it is a bipolar power. So I'm just focusing on my unipolar side. Okay, monopolar side, this side only. So here, if it is 500 megawatt, half of the power will be transmitted from upper part, half of the power will be transmitted from lower part. Okay, so if we can expect that the half of the power of bipolar, that is 1500, that is 750 megawatt. Okay, so 750 megawatt is the power flowing from one end to another from the monopolar side, half of. Now if you calculate the current, you will get ID. That ID is how much current is flowing. So you can expect 750 megawatt divided by 500 kV. So that will be your current. Okay, so line loss. So line loss will be, so this line loss is per pole 5 ohm. So one pole has a resistance of 5 ohm. So other pole, so this is one pole. The other pole is here. So if you can expect the line losses, so you will get ID. Whatever ID you get, ID square into R. ID square into 5. That's the line loss expected here in this side. Okay. So this is the line loss. Now next is the inverter and DC voltage. So inverter and DC voltage means this side voltage, okay. So inverter and DC voltage. So here you can apply the KVL part. You can apply the KVL, and how you will apply the KVL. So one side you have 500, and there will be a loss, and this loss on the in the transmission line is I into D. Okay, ID into R. So this is the loss. So if I want to calculate UD2, so this is UD2. So UD2 is 500 kV minus ID into R. So this is a calculate ID multiplied with R, that is the voltage difference. So it is that. Now DC power delivered to the inverter side. Now you can calculate this, how much delivery is done. So for a monopole, I'm just focusing on monopole side. So total power that is generated is 750 megawatt. Okay, 750 megawatt, that is coming from monopole, and then there will be a loss in one pole. One pole loss is id square into r. So this is the loss that is coming in picture in one pole. So here it is saying that delivered to the inverter side. So this is the loss, and if you multiply it with 2, so that is your total bipolar power bipolar power. Okay, so this is your bipolar power that is transmitted from your in a bipolar transmitted from a rectifier side to the inverter side. Now next is your DC voltage of 6 pulse converter at the rectifier. So whatever you have calculated right now, it is for your 12 pulse converter. Okay, now if you have to calculate for a 6 pulse converter, just half that, and that you will get the. So here 6 pulse converter at rectifier end. So rectifier end you are having 500 kV. Okay, 500 kV for 12 pulse. For 12 pulse 500 kV. Now if you have to calculate for 6 pulse, then you have to do half of that. Okay, so 500 kV divided by, so that will be 250 kV. Okay, so this is your rectifier side. Similarly, DC voltage of 6 pulse converter at the inverter end. So you have already calculated DC voltage at the inverter end, the third part. Now if you half of that will be your UD2 divided by 2. Okay, so this is your 6 pulse converter. So this is DC inverter and DC voltage is of 12 pulse converter. Half of that will be this. Okay, next is your bipolar DC voltage. Bipolar DC voltage, at which end we are talking, and that is your at rectifier end. So bipolar means double. Okay, bipolar means double of the DC polar. So this monopole has 500 volt. So double of that 500 volt is coming from here. So bipolar DC voltage is 1000 kV. So this is the double of that voltage. Okay, similarly bipolar DC voltage at the inverter side. So whatever you are getting as UD2 double of UD2, 2 times UD2, that will be your uh, bipolar DC voltage of the inverter side. Okay, I hope this is quite clear. We'll move on to the next part. So now we'll start our unit 3, and in the last lecture I have given one problem, and regarding that problem here in this here I have given that we need to find out the uh, power angle equation power angle equation of this figure, and there I have done that there is a 3-phase fault occurring here at point P. Okay, now if a three now here if a 3-phase fault occurs, then at the middle of the part, so half of the reactance goes this side, J 0.4, and half of 0.2, and half of the reactance comes this side, 0.2. Now at steady state condition I have analyzed that the power or the voltage, sorry, the voltage of your generator voltage is 1.05, and the delta initial angle is 28.44. Okay, so I have already analyzed this the part. Now this I'll extend this part for our further analysis, and for our further analysis means I will create a 3-phase fault, and you have done, some of the people have done this problem but using their method. Now I will do it using a different approach. What I have done, that is our Y bus matrix approach. Okay, I have created that Y bus matrix and then find out. So before that, creating a Y bus matrix, I will change these reactances into admittances. Okay, so here if you see, the reactance is 0 point total reactance. I'll convert, so I'll make it like this. So this is my reactance, and the overall reactance of this 0 J 0.2 plus J 0.1, that will give you J 0.3, and if you take the inverse of it, admittance will be So you can do 1 upon j 0.3. So you will get minus j 3.33, right? So this is the admittance. So I will write it minus j 3.33. Similarly, further you can do the reactance of the other two. So you will find out that reactance of this will be j minus j 2.5. Okay, here also minus j 2.5. Now what I've done, so this is my reactance here, it is minus j 2.5. Okay, and I'll, as there is a fault, so what I'll do, I'll create a fault here, and here also one half of the reactance comes with the fault. So here after the fault you will have this part will be j, or better do it like this. uh, so here it will be like this. So this is your j minus j5. Okay, and this is also minus j5. So this j5 and j5 comes when you inverse j 0.2. So 1 upon j 0.2 you will get 1 upon j 0.2, you will get these two. So overall the circuit changes like this, right? So this is my circuit right now after the fault. So the fault is present and my admittance circuit is like that. Now what I will do, I will specify the bus. So this is my bus number 1 and this is my bus number 2. Okay, and this is my bus number 3. Okay, so this, there are three buses, and out of these three buses, 1 and 2 bus have its own generator. Okay, the generator bus is present at 1 and 2, but 3 does not have any generator, so there is no energy at 3, right? No energy system is at 3, neither there is a load, it is simply a transmission. So we'll frame out first the Y bus matrix from this, and then we will do the further parts. This is the Y bus network which we have formed. Next is that Y bus. Next we have to form our Y bus matrix. Now this Y bus matrix contain I current in one side, then you can say Y and then multiplied by V. Okay, so matrix multiplication in the way this form. So here I can write I1, I2 and I3. So these are the current of your bus 1, bus 2 and bus 3. Now next, this is the Y bus matrix, then bus 2, bus 1, bus 2 and bus 3. So this is my matrix actually. Okay, now we have to form our Y bus matrix. Now if you see the Y11 is the self admittance of bus matrix, and that is your minus j 3.33. Okay, next Y12. So the whether there is a common matrix or admittance between 1 2. So there is no any common between 1 2. So there is no Y12. So it will be 0. Okay. Next is Y13. So Y13, it has one admittance matrix, that is um, J 3.33. So remember that when you have a mutual admittance, that is Y Y13 y13, if you have to write, you have to actually multiply or have a product with a minus sign, and then you can make it. So actually the y13 is minus j3.33. Just you have to multiply it with the minus sign, then you can present. So mutually you have to multiply. For a mutual admittance you have to multiply with a minus sign. Okay, you have learned this framing in your load flow analysis, so I am not going to analyze or discuss in this. Okay, next is your uh, next is your y21. Okay, y21 again 0. y22 has, on this bus if you check, there are two self react admittance. The two admittance are connected, that is this and this. So so this is a minus sign, so you can add these two, so you will get j 7.5. So that is 7.5 minus j 7.5. And then for 3 2, okay, for 3 2, this uh, j minus j 2.5, and then you have to multiply with the minus sign, so you will get j 2.5, j 2.5. So for mutual things you have to multiply with the minus sign. For a self you don't have to multiply with the minus sign. Okay, next is 3 1. So 3 1 will be j33. Next is your j 2.5, and just next is 3 3. Okay, y33. So y33, add all the admittance that are connected on third bus 3, so you will get j minus j 10.83. Okay, so minus j 10.83. So this is the overall y bus matrix. So for mutual you have to add the matrix or admittance on that bus. For your for mutual you have to just have a just have to mi have to multiply a minus sign, and for yourself you have to add all the matrix. So that's why you can frame this. Now here the matrix. So once you framed the y bus matrix, I am interested in some other calculation. So I can write this y bus matrix like this: I1, I2 and I3, and that is multiplied by y11, y12, y13, y21, y22, y23, y31, y33, y32, y33, right? So I can write this matrix like this: v1, v2, v3. So if you find out uh, the third bus does not have any voltage bus, so there won't be any incoming current, extra incoming current that can come from here. So I will write I3 is equal to 0, no incoming, because it does not have any source. Okay, so what I can write, I3, if I am writing it as 0, so I'll write it like this: y31 v1 plus y32 v2 plus y33 v3, y33 v3 equal to 0. And if you equate, if you do some, I can write v3 is equal to minus y31 upon y33 v1 minus y32 upon y33 v1 v2. Okay, so this is how I will reduce. Why I am doing this? Because I want to reduce this 3 by 3 matrix to 2 by 2 matrix. Why? The reason is because I am not interested in bus number 3 because it does not have any source. Okay, so reduction is done based on the source. So make sure when you are calculating the transient analysis, try to reduce your matrix. Okay, so what I can write next is V3 is this form. So putting this equation in the first two. So first two is I1 is equal to Y11 plus Y11 into V1 plus Y12 into V2 plus Y13 into V3. Okay, so in V3 place just put this equation here in place of V3. So you will get, and you just equate and simplify, you will get this equation Y11 minus Y13 Y31 upon Y33 V1. Okay, and plus Y12 minus Y13 Y32 upon Y33 V2. So you will get this equation, and similarly if you put I2 put like this equation, that is your Y21 V1 plus Y22 V2 plus Y33, sorry, Y2, so Y23 V3. So if you put the same V3 here again, put the same V3 here again, and you will simplify, you will find out I2 as Y21 minus Y23 into Y31 upon Y33 into V1 plus Y22 minus Y23 multiplied by Y32, okay, and divided by Y33 V3. So this is how I have written, I have reduced I have equated this third equation to 0, and I have reduced this form to 2 by 2 matrix. I will show you again. I will make the matrix form, and then I can write those things. Okay, so I have reduced the 3 by 3 matrix to 2 by 2 matrix. You can find out. So now here I am representing y11 as y11 dash, y12 dash, y21 dash, y22 dash, and I can write y12 y11 y12 like this. How I have derived, you can check it. Okay, now putting all the values and everything of the previous, I have calculated y11 y31 y2 like this, and so I will modify, I can modify this thing. I can write, okay, so I can modify this thing like this: minus j 2.308, okay, j 0.769, j 0.769
and minus j 6.923. So this is how the matrix have been reduced, and these are the values. Just calculate these values, and if you want to find out the maximum power or P max during the fault. Now during the fault, if you want to find out, and as this the during fault, okay, so P2 I'm writing. So what I can write, voltage is 1.51, so EV upon XS, right? So now this is in admittance, so V1 V2 into Y12, and this Y12 will be the dash part, okay, new Y12. Now if you write 1.05 multiplied by 1 into y1 dash is j 0.769. So we'll calculate and you'll get 0.808. Okay, so this is my maximum power how I'm calculating using. Now this method is quite feasible, and this I hope that all of you will do like this, okay, because the older method you have to reduce the circuit a lot, okay. Once you have to, what you have to do, you have to calculate the uh, this equivalent, convert it into star, and then convert it into delta if you have done it, okay. You have to use star delta mechanism. So to avoid that, better do some calculation and then you can use it. Now this is how, this is the power. Now if I want to calculate the accelerating power, as I know that our delta was operating at 28.44, okay, delta initial angle. Now accelerating power, if I want to find out, so I can write it that during first this accelerating power is PS minus P2. So PS was 1 mechanical power and P2 will be 0.808 sine delta 0. So you put the value of sine delta, you will get the accelerating power. Okay, so you will get, I think, 0.615 like that per unit. Put the delta here, you'll get it. And if you want to put in form of what you will say, this in the form of power angle equation, you can write 5 upon 5 is the MVA, H megajoule per MVA. Okay, 5 is H, 180 F can be 50 d square delta upon dt square, and that I can write accelerating power 0.615. So this is my accelerating power. So acceleration, if I want to find out acceleration of the rotor acceleration, so you can put 0.615 into 180 F upon 5. Okay, so this is the accelerating power. So here I'll end this class today here, and I'll give you some numerical to try on yourself, and or do one more same issue problem, like what happens if the circuit breaker clears it. Circuit breakers clear the fault, clear the fault. Okay, what happens if the circuit breaker clears the fault? So do this thing, the third part, and write your answer in the Google class. Okay, thank you.